Mag at the IAC today. And today he's going to tell us about longitudinal magnetic field in an active region plage from the photosphere to the upper chromosphere. So whenever you're ready, Tanausú.
Okay. Good afternoon, everyone. Thank you for the presentation. And thank you, of course, also for the invitation and the opportunity to be back at the HAO Colloquium to give a talk, even if it's not literally back. So can you see my presentation?
Yes.
Okay. As Paul was saying, today I'm going to talk about the mapping of the longitudinal magnetic field in a plage of the active region from the photosphere to the upper chromosphere, and in particular of a plage of the active region 12738 on 11 April 2019. That was the one that was observed by the class to explain. So let's go into it. There are many reasons why we could want to study the sun. We might be interested in the connection with the Earth's climate. We might be interested in space weather. We might want to study the sun as a main sequence star, or it might be just for laboratory for plasma and quantum physics with physical conditions that cannot be reproduced in laboratories at Earth. But what all these topics have in common is the importance of the magnetic field. So the magnetic field plays a key role in the physics of stellar atmospheres, including, of course, the solar atmosphere. It is responsible of the solar activity. It forms the plasma structure of the outer solar atmosphere. It's key to explain the existence of the hot corona, and it's also important for the shaping of the space weather. However, these magnetic fields are elusive. They are difficult to detect and to measure. And one reason for this is that the effects on the intensity profiles are, in general, quite negligible. And the magnetic field information is then encoded in the spectral line polarization that in the sun is typically produced by the Zeeman effect and the scattering polarization and the Hall effect. So a quick reminder about polarization. The polarization tells us how the wave of the electromagnetic wave is oscillating. And this oscillation, in turn, contains information about the plasma that emitted this radiation. We characterize the polarization with the 4 Stokes parameters, where Stokes I is just the intensity that represents the total amount of energy that the electromagnetic wave is transferring. And then the rest of the parameters are defined as the difference of oscillations in orthogonal direction. In this way, Q and U define the linear polarization, and V defines what is the circular polarization. It is important to know that the polarization is present when there is a lack of asymmetry. And in the sun, the typical processes to produce this polarization is the scattering polarization. It is due to radiation pumping by anisotropic radiation, by the Zeeman effect that is produced by the breaking of the degeneration of atomic soot levels in the presence of a magnetic field, or by the Hall effect that is just a relaxation of the quantum coherences of an atom. In this talk, because we are interested in the longitudinal magnetic field, we are going to focus on the Zeeman effect. To have also a quick reminder about the Zeeman effect, we are going to consider a two-level atom with angular momentum 0 and 1. And we know from atomic physics that this level is in fact 3 different levels with magnetic quantum numbers -1, 0, and +1. And they, in the absence of any external force, are degenerate. That means that they have the same energy. Therefore, we have the 3 magnetic components in the same wavelength. In general, we expect that they are equally balanced, so we don't observe any polarization. However, in the presence of a magnetic field, the degeneracy is broken. There is a shift of the energy of the levels, and the different magnetic components are shifted also in wavelength, following this equation here. We see that the shift is proportional to the magnetic field, the square of the wavelength, and the effective and the factor of the line that depends on the quantum numbers. In this situation, if we were to observe in a line of sight that is parallel to the magnetic field, we would observe circular polarization that typically has these antisymmetric features. And if we were to observe in a line of sight perpendicular to the magnetic field, we will see linear polarization that typically has this three lobes structure. Of course, in any other line of sight, we will see a combination of the two of them. It's important to remember that typically the circular polarization scales with this quantity R, and the linear polarization scales with R squared. With this R is the ratio between the Zeeman splitting that we saw before and the Doppler width of the line. And in the typical conditions of the sun, this ratio is lesser or much lesser than 1. That means that we expect that the circular polarization signals are much more prominent than the linear polarization signals, at least with respect to the Zeeman effect. So if we want to study the magnetic field in the outer atmosphere, that is the ionosphere and the transition region, we need to find spectral lines that form in these regions and that are sensitive to the magnetic field. These spectral lines are typically in the far ultraviolet. For example, we have the neutral hydrogen Lyman alpha, the silicon 3 resonance line that is very close to Lyman alpha, the magnesium 2 H and K, or the oxygen ultraviolet 3, that is the resonant multiplet of this ion. However, the problem with the far ultraviolet is that it cannot be observed from the ground because the Earth's atmosphere absorbs such radiation. So we have two options. We can go to space. Those are long missions and they suppose a significant cost. Or we can go suborbital, that are very short missions, typically of minutes, but they are much cheaper and much easier to be accepted. And to this group of experiments is where we found CLASS. CLASS, that stands for Chromospheric Lyman alpha spectropolarimeter, measure the intensity of linear polarization in the Lyman alpha line of the neutral hydrogen. This experiment was motivated by the theoretical investigations of scattering polarization and Hell effect in this spectral line, and it was successfully launched on September 2015. However, what we are interested in this talk is in Class 2. Class 2 stands for Chromospheric Layer Spectropolarimeter and is a reflight of the same rocket. And this second time, it measured the intensity, the linear, and the circular polarization, this time in the region of the spectrum of the magnesium H and K lines, that is around 279 nanometers. This experiment was motivated by theoretical investigations of scattering polarization and the Halley and Zeeman effect in the magnesium 2 H and K lines, and it was successfully launched on 11 April 2019. This was an international collaboration of several countries, the USA, France, Japan, Spain, Czech Republic, Norway, and Sweden. And this is a picture of the instrument. Here in the panel below, we can see the optical path, where the red names indicate what changed in the reflight. That is what wasn't there in Class 1 or had to be changed because of the shift in the wavelength. So the instrument had a Cassegrain telescope of 27 centimeters of aperture, then the rotating waveplate, that is what caused the modulation of the radiation, and then we had the slit. The radiation that doesn't go through the slit goes to the slit optics, that because it's the same that in Class 1, it measures Lyman alpha, and the radiation that goes through the slit goes to the grating. The grating works both as a splitter in the spectrum and as a beam splitter, and it directs the light into symmetrical channels. Then there are two analyzers of polarization that are 90 degrees one respect to the other, and finally it reaches the cameras. Both cameras are able to measure the full Stokes parameters, IAQ, U, and V, independently, but they can be combined together in order to increase the precision and avoid systematic errors. So in this launch, Class 2 had two targets, Class 1 at the center for calibration purposes, and one of them was in this flash region, that was the early active region that was around at that time, and one for the limb. And here we're interested in the flash region. This is the image of the slit yaw in Lyman alpha, and this orange line represents the slit. You can see that most of the slit crosses the flash, and a portion of the slit falls in the white sand. And you can see that there are two network elements that the slit grows here, and we will see that there is magnetic field tension in those elements. So this is the spectrum reduced and added in the 2 minutes and a half of observational time. And for this talk, we're interested in particular in Stokes I and Stokes B. Here we have the resonant emission H and K lines with its characteristical intensity profile of 2 emission peaks and a central depression. We can see that they have quite remarkable signals in the circular polarization, at least in the plus region, that is here. And we found more interesting lines. This was not planned, but when reducing the data, we saw that there were some strong signals in between the H and K lines, and those corresponded to some neutral manganese lines. So what we did in this effects analysis was to apply the weak field approximation to the circular polarization of these lines. So its Zeeman splitting is much smaller than the typical width of the central line, and the longitudinal magnetic field can be considered constant with height in the region of formation. We can write the linear polarization following this equation. In this approximation, the circular polarization is proportional to the effective length factor, the square of the wavelength, the longitudinal magnetic field, that is the quantity we want to infer, and the first derivative of the intensity. Here we have the lambda factors of the lines that we analyzed. We can see that for the magnesium, the lambda factors are pretty close to 1, with the H line being larger, so we expect larger signals in this line. And for the manganese, the lambda factors are much closer to 2. And again, this one is larger, so we expect larger signal in this line than in that. We have to check if the weak field approximation can be applied. And for that, we have to compute the ratio between the Zeeman splitting and the Doppler width. And it's proportional to this quantity here, where this is the Boltzmann constant, temperature, mass of the atom, the microturbulent velocity, and the magnetic field. So assuming no microturbulence and conservative values of temperature and magnetic field, you obtain ratios of 0.06 for the magnesium and 0.3 for the manganese. Those are going to be upper limits for this quantity, so we are safe to assume that these lines are in the weak field region. So in order to test how well the weak field approximation fits the circular polarization profiles, we did some simulations. We used the Hadley-RT code that is able to perform the non-local thermodynamical equilibrium polarization transfer. It includes atomic polarization, although this is mostly linear polarization, and is able to include quantum interference and frequency coherence, that those have the partial frequency distribution effects. And these are important for the patterns, not only for the intensity, but they also have an impact in the circular polarization. It can take into account the incomplete Paschen-Mach effect, and this code works with 1D and atmospheric models. So we took some semi-empirical models, in particular the one for representative of the average quiet sun and of a flash, and we added ad hoc magnetic fields in order to have information on how the polarization profile is modified when we change such magnetic field. So let's go atom by atom. First, we have the magnesium. This is the level structure of the magnesium atom. It's the lower level, and the first excited levels are the upper levels of the H and K line. We also include the subordinate lines because they are in the same spectral region. Here we have the K line, two of the subordinate lines that are completely blended, and the other that is here at the left. However, take into account that the class spectrum range reached around this wavelength, so this line was not observed. And regarding the other subordinate lines, due to the blend, the applicability of the weak field approximation is not very good in the inference of the magnetic field. So if we add homogeneous, and that means constant with high magnetic field of increasing amplitude, we get circular polarization profiles of this shape. We can see that it's characterized by two pairs of loads. We call this one the inner load, and this one the outer or stable load. And here in the bottom right, what we are plotting is a response function of Stokes B to the magnetic field. That is how the circular polarization changes when we do a small perturbation to the magnetic field. What we can see here is that for the wavelengths of these two peaks, the region of sensitivity is the top part of the model, around 2 megameters. This corresponds to the upper chromosphere just below the transition region of the model considered. And for the wavelength of the outer lobes, that are this here, we get a much wider region of sensitivity, around 1,400 kilometers. That corresponds to the middle chromosphere of the atmospheric model. What can we conclude from this? Well, the ratio of the amplitude of the circular polarization loads between the inner and outer one gives us a ratio of the longitudinal magnetic field at these different heights in the top chromosphere of the model and the middle chromosphere of the model. However, this application to an homogeneous magnetic field is not that interesting or realistic, so we apply it to different stratifications. So we do the same than before, an homogeneous magnetic field of 200 Gauss, and we also test it with a decreasing and increasing stratification of the magnetic field. We see that, as expected, the ratio between the inner and outer lobes changes when the ratio of magnetic fields also change. And if we apply the weak field approximation, that is, we compute the Stokes B profile as the derivative of the intensity times all the proportionality constants, we get these red lines. We can see that the fit is quite good in most of the profile, but in the outer lobes of the profile. And this is even in the case where we have an homogeneous magnetic field. That is, we are completely sure that the magnetic field that corresponds to the black line is 200 Gauss. What does this mean? Well, we are going to retrieve the longitudinal magnetic field from the observation, because the weak field approximation overestimates the signal, the inference is going to underestimate the longitudinal magnetic field. So no matter what, when we apply the weak field approximation to this profile, we are going to subestimate the longitudinal magnetic field for the outer lobes of this profile. So what we did in the analysis in the paper was to split the profile in two. This central part we call the core, and the two at the side, the wing part. And we apply the weak field approximation separately to these two regions. And here below, we show what is the inferred magnetic field. Now, in the background, we can plot the contribution function that gives us an idea of where this circular polarization profile is coming from. And we can now see how good is the inference. Starting from the homogeneous one, in this case, the height doesn't matter because it's constant. We see that the core gives us 202 Gauss. That is pretty close to the original magnetic field of 200 Gauss. But the application to the wings gives us 160 Gauss. Therefore, we have an underestimation of around 40 Gauss, even in the easiest case. Now, as we go to the decreasing magnetic field, we see that the inner lobe should be sensitive to magnetic fields around 2 megameters. The inferred magnetic field is around 7 Gauss. Then we see that it's pretty close to the value around this region, that is around 10 Gauss. And for the wings, that should be sensitive around 800 kilometers, we get, I cannot actually see the number because there is a label there.
So you can see if you click the hide thing, should get rid of, yeah.
Okay. Sorry. It's 85 Gauss, that is around here, and we see that the actual magnetic field is around 120 Gauss. So again, we have an underestimation of around 40 Gauss in the estimation of the longitudinal magnetic field using the wings. And lastly, in the last case of the increasing magnetic field, again, we expect sensitivity around 2 megameters, and we infer 30 Gauss. We infer 180 Gauss. That is pretty close to the magnetic field in this region, in the top part of the model. And from the wings, that should be sensitive around 800 Gauss, we get 13 Gauss. So underestimation of around 20 Gauss in this case. So what we can conclude? Well, the inner loads give us an estimation of the longitudinal magnetic field of the higher layers of the model, while the outer loads should give an idea of the longitudinal field at the middle chromospheric heights. But we have to take into account that it's going to be always an underestimation of the actual longitudinal magnetic field. Now we can do the same with the manganese, but we'll have to take into account that it's a minority species with non-LT effects. In general, this type of ions require quite big atomic models in order to determine intoxication state. So what we did was to take all the available manganese 1 and 2 levels and transition data with LS coupling information from the NIST database. Then we used some approximations to compute the photoionizations and collisions. And although we know that the atomic model can be improved, taking some experimental collisions or improving this approximation, it is enough for the purposes that we were doing in this analysis. So these are the atomic levels that we considered, with some 100 levels and transitions. The levels are represented by these horizontal lines, and the solid lines are the radiative transitions. Take into account that every level is connected to every other level via collisions, but we didn't draw them here because we would see nothing. And here is the transition we're interested in. We can see that it's a resonant transition because it starts in the ground pair of this ion, but it doesn't go to the first excitation state. One important thing about this transition is that they are formed between the H and K lines. Due to the partial redistribution effects in the magnesium, the continuum in this region is shaped by the magnesium lines. That means that in order to correctly reproduce the intensity profiles, and that means to correctly reproduce the derivative of the intensity profile, we need to take into account at the same time the magnesium H and K lines with PLD effects and the manganese lines. And here I show you the result of one simulation. The manganese multiplied are these three, the narrow ones, and below what I show is the contribution function for the intensity. That gives us an idea of what is the region formation of the lines. We can see that the manganese is here around 800 kilometers. So the circular polarization is going to be sensitive to the longitudinal magnetic field a bit below, and that corresponds to the lower chromosphere of this empirical. However, what happens with the manganese is that we have one single isotope with nuclear spin 5½ That means that this is an ion with hyperfine structure, and we don't have 4 levels and 3 transitions. We actually have 22 levels and 42 transitions. When we have hyperfine structure and we are dealing with magnetic field, it's important to have a look at the NAV diagrams. That is how the NAV changes with increasing magnetic fields when we are taking into account the hyperfine structure. These are the NAV diagrams of the lower level and the 3 upper levels. In solid lines, we have the calculations taking into account the Paschen-Mach effect, that is the quantum coherence between different F states, while the dashed gray lines are in this linear schema regime, that is ignoring any quantum interference. Because the 3 upper levels are quite similar, we are taking just one of them. And what we can see here is that for the upper levels, we start seeing repulsions and level crossings at values of 80 Gauss. And for the lower level, we see repulsions as soon as 10 Gauss and level crossings as soon as 30 Gauss. What does this mean? Well, in principle, it is necessary to consider the Paschen-Mach regime. But the problem is that we do not have yet any code that is able to include the wings of the magnesium 2 with partial resolution effects, and the hyperfine structure of manganese in the Passion back region at the same time. So we did some initial experiments assuming the linear symmetry. We did the same. We added ad hoc magnetic fields to the magnetizing empirical model, and we wanted to answer the question of what is the impact of the hyperfine structure on the circular polarization profile. And this is what we are showing here. The black solid line is the calculation without hyperfine structure, and the dashed black line is the weak field approximation applied to this intensity profile. And we see that if there was no hyperfine structure, the fit would be quite good. Now, if we include the hyperfine structure, we get the solid red curve. The first effect that we see is produced by the shift in the hyperfine structure. That makes the intensity profile well, and this translates in a shift in the peaks of the fit profile. But what also happens is that the signal of the circular polarization is decreasing. So if now we were to apply the weak field approximation to the solid red curve using the Landé factors of the fine structure, we will significantly overestimate the signal. However, it was still important to study the impact of the missing F-state interference. So what we did was to solve the problem without hyperfine structure with the magnesium 2 and manganese 1 lines using the hand-like code as before, but we took every output of the code and we transformed it to the input of a two-term atom numerical code with J and F state interference. And we compute just the intensity and the circular polarization profile. And this was the result. The red curve from before is now blue. Set A means a linear Zeeman approximation. And now if we include the quantum interference, we have the black solid line, the incomplete Passion back effect. And we see that what happens is that the F-state interference increases back the signal. So if now we apply the weak field approximation using the Landé factors of the fine structure, we get the dotted line, and the fit is again quite remarkable. So the conclusion is that the weak field approximation seems to fit the circular polarization profile in our test. So the weak field approximation can be applied as if there were no hyperfine structure. And this is a consequence of both the principle of spectroscopic stability and the fact that the hyperfine structure shifts are very small in comparison with the width of the spectral line. Because we know that these multiplet forms in the lower chromosphere, the weak field approximation is going to give us an idea of the longitudinal magnetic field at those layers of the solar atmosphere. So now we have, from the class data, information to be able to extract the magnetic field at 3 different layers in the chromosphere. So if we had some photospheric data, we would be able to complete this determination with a lower height. And this was achieved because at the time, during the class observation, there were coordinated observations with Pino. These observations with the fast mode were performed in this pair of iron lines in 630 nanometers. And what happens with this line is that in the photosphere, we expect magnetic fields that are generally strong. They can be of the order of kilograms. So in this case, the weak field approximation cannot be applied. What we did for the photospheric data is to use the level 2 data from the zigzag of HAO, and this one is obtained from the application of a Milne editor inversion code, in particular the Milne code. Once we apply the code to the full field of view, we degrade it to the class 2 resolution, and we then took the magnetic fields along the slick. In this determination, we assume that there was no significant degeneracy between the filling factor and the magnetic field, because remember that this code inverse an equation of this type, where the magnetic field only fills a fraction of a pixel, represented by this F. And under this assumption, what we retrieve from the code is the longitudinal magnetic field. And as a reference, the typical filling factors found in the inversion were between 0.2 and 0.95. So we are in a position to apply the weak field approximation to the actual class 2 data. So remember that we have the application to the core of H and K lines. This will give us the magnetic field in the upper chromosphere. We cannot use the wing of the K line because they are blended with a neutral iron line, and that makes it not antisymmetric. But we can use the wing of the H line to get an idea of the magnetic field in the middle chromosphere. But remember always that it's an underestimation. And for the manganese, we can use the Lambda factors. We forgetting about the hyperfine structure, and they will give us an idea of the magnetic field in the lower chromosphere. So here in the left, we have the slit yaw of slash, and this is the slit of the spectrum. And here I'm going to show some of the profiles in different positions of the slit. The first sample is the B point that had the characteristic of having a local minima in the magnetic field of the photosphere. We see that the fits are quite good in the three cases. For manganese, the core of the lines and the wing of the H line. And we find magnetic field of 230 Gauss, 200 Gauss. And remember that because this is an underestimation, this should be also around 200 Gauss. So we find a point where the magnetic field in the photosphere is below 200 Gauss. And in the lower to upper chromosphere, we found magnetic fields around 200 Gauss in the three layers. Here we have the C point, that is one of those where the magnetic field in the upper chromosphere was the strongest. And we can see that we reached values of 300 Gauss just below the transition region. And lastly, this D point is one of the network, and we see that the signal in the core of the H and K lines is quite small. In fact, it is compatible with zero magnetic field, while there is still a measurable signal in the wings of the H line and in the manganese lines. So we can get a magnetic field of significant amplitude above 100 Gauss in the middle and lower chromosphere, but almost nothing in the upper chromosphere. So if we apply this procedure to every pixel along the slit, this is what we have. In this figure, the bottom panel is just a zoom of this region to better visualize the positions around zero magnetic fields. To the left, we have longitudinal magnetic field. In the right, we have intensity, that is this solid gray curve, that is intensity in the center of the K line, and this dashed dot curve, that is intensity in the blue peak, or the blue emission peak of the K line. The colors are the inferred longitudinal magnetic field, with green for the photosphere, that is the one obtained from anode. Blue for the lower chromosphere, that is the one obtained from the manganese. Black for the middle chromosphere, that is the one obtained from the wings of the H line. And red for the top of the chromosphere, that is the one obtained from the core of both the H and K lines. And what can we extract from this figure? Well, the first thing we see is that if we look only at the region covered by the plush, that is the one inside this square, we see magnetic fields of a single polarity. There are two possible exceptions in these two positions, but these are below 1 sigma, so they are not statistically significant. So at least along our slit, the plush shows a single polarity. Then in the photosphere, we find strong concentrations of magnetic field. And in these concentrations, we see that when we increase the height in the atmosphere, that is going from green to blue to black to red, the magnetic field monotonically decreases, the width of these structures increases, and the overall spatial variation also decreases. Then in these regions where we find the minimum of the photospheric field, we see that it is below the chromopheric field, and these chromopheric fields are quite similar between lower, middle, and upper chromosphere. In the longitudinal magnetic field, there is an increase in the intensity, both in the core and in the wings. And to pursue more this kind of correlation, what we do was to take the intensity data, and we use the IRIS² database to do an inversion of this intensity. And what we are plotting here is the magnetic field in the middle and upper chromosphere, and the electron pressure that resulted from that inversion. And we can see here that it also shows a quite remarkable correlation at eye level. And what we show here is the actual correlation indexes for these quantities at the different heights. CI stands for correlation with intensity, where K3 is the center of the K line, and K2P is the blue emission peak, while CP is the correlation coefficient for the electron pressure. And we can see how this correlation increases when going up in the atmosphere. And for the top of the atmosphere, we see a significant correlation between these quantities. In particular, there is some correlation with the electron pressure that is related to the heating processes. So let's now summarize in some conclusions. So the weak field approximation could be applied to the magnesium HAO line and the manganese 1 multiplet around 279 nanometers to infer the longitudinal magnetic field at different heights in the solar ionosphere. It was applied to the class 2 data, and by analyzing the inferred magnetic field, we could conclude the following. Regarding the clash, we found that it had a single polarity. Regarding its photosphere, we found there the strongest fields, and they were organized in small regions with some magnetic concentrations of the order of kilogauss, separated by a small region of few gauss, and these regions were about 10 arc seconds. In the lower chromosphere, we found variations at a similar scale, with smaller amplitudes, and we found magnetic fields of around 700 gauss. For the middle and upper chromosphere, the field went from 0 to more than 300 gauss. It shows smooth spatial variations, and the field inferred at the upper chromosphere, it was not much weaker than those found in the middle chromosphere. However, take into account that the latter are always an underestimation. That means a lower limit for the actual field. So we found that at the photospheric field local minima, these fields were smaller than in the chromosphere, and at the chromosphere field local minima, we got similar values for the three layers. That means from the lower, middle, and upper chromosphere. We also found that the spatial fluctuation of the field decreases with height, and all of this together can mean that the magnetic field in the photosphere is highly structured with strong and weak field variation, and it expands rapidly, making it spreading horizontally in the overlying chromosphere with magnetic fields that are weaker and with a smoother variation. We also found remarkably high correlation between the longitudinal magnetic field in the top layers of the atmosphere and the intensity at the center and the peaks of the magnesium 2K line. There was also substantial correlation with electron pressure, and this strongly supports the idea of the magnetic origin of the heating in the upper chromosphere in the active region flash. Regarding the network, the class 2 slit crosses the network twice. There we found photospheric fields in both locations of about 200 Gauss with opposite polarities. We found magnetic fields of 80 and 160 Gauss in the middle and lower chromosphere, but the inner lobes of the magnesium HAK lines were very weak and were compatible with 0 Gauss. And we checked that this was not due to signal cancellation during the 2.5 minutes of observation. So the magnetic field in the upper chromosphere must be then below 10 Gauss, the longitudinal magnetic field. And this can lead to 3 possible scenarios. The first of them is that the magnetic loops of the network do not reach the very top of the chromosphere, so we wouldn't be able to see magnetic field because there is not. The second scenario is that the magnetic field in the upper chromosphere of the network are too weak to be detected by the Zeeman effect in these magnesium resonance lines. So this will mean that the magnetic field reaches these high layers, but is too weak to be detected. And the third scenario is that the magnetic field in the upper chromosphere of the network becomes nearly perpendicular to the line of sight of the class observation. So the magnetic field can reach the upper chromosphere with a significant amplitude, but we would be blind to this field because of the geometry. And in principle, from this analysis, we cannot distinguish between these 3 scenarios. So what's to come? Well, of course, there is a lot of very interesting and excellent data from the class 2 observation, and further analysis is due. In particular, right now there is an advanced inversion code being under development that uses the High-Altitude code as a forward solver, and we want to apply it to the force touch parameters in the flash. And we cannot forget that we have some interesting quasar and dark data that should be also analyzed. Then there is class 2.1, that is basically class 2 in 2D. It's going to be a reflight of the very same rocket, but now we are going to do a raster in an active region. And this experiment has been already approved, and its Ionosphere is going to be launched this year in autumn. And in regards to the study of these ultraviolet regions that has shown very potential diagnostic qualities, it's going to be we are writing proposals to new instrumentation, in particular solar cubes that was already presented, Struve, that is also a small telescope, and the larger project that is CIMEX. And I'm sure that you are familiar with these 3 ones because they are an initiative from the High Altitude Observatory. And with this, I have finished the talk. Thank you very much for your attention. And if you have any question, it would be my pleasure to answer.
Thank you very much. Okay, so does anyone have any questions? Let's go to Juliana first.
Hi, so I have some question about the network interpretation. If you can go back to the slide when you have the 3 possible explanations for that. And actually I have 2 questions. The first one, if you can point your slit at different position on the disk near the limb and near the center, you should be able to test the number 3, right? To see how much of the line of sight is actually affecting that. And my other question is for the magnetic loop that don't reach the top of the chromosphere, can simultaneous observation, the high resolution in the chromosphere and following these loops and this structure help you to also to answer that and roll it out or confirm it?
Yes, regarding the third point, the issue is that this network is close to the active region. That's the reason why it shows these significant magnetic fields. The other observation was much closer to the limb and in the very quiet sun, and there was no, the circular polarization signal is not that significant in that other observation. So that doesn't work to rule out this one. Regarding the simultaneous observation, the class 2 is the only observation of circular polarization in that region, so there is no other one to compare with. So hopefully the relaunch of the mission will work in this regard. We will have another observation at a different time where we can check if we actually get the same.
And to follow up, but if you have like an instrument that can follow, for example, the instrument in space, and you can follow the same active region from the limb to the disk, you should be able to rule out the 3 or verify the number 3, right?
Yes, and that would be excellent. And that's our dream, to have a telescope that is permanently there and not just 5 minutes.
Okay, Ricky?
Ricky, you're muted.
Okay. Yeah, just thanks for the talk. Really liked it. So you only got 5 minutes of time out of the atmosphere. Was that all for one exposure, or did you get 2 exposures so that you could do like a comparison of some dynamics at all?
I mean, the flash was observed within 2.5 minutes, but the cadence of the observation is 3.2 seconds. So we have frames each 3.2 seconds. So technically, we could do studies of the 10 series. However, of course, the shock there is the addition of images, the more noisy they are going to be. So that's the reason why in this paper we decided to take the full 2.5 minutes, because we checked that there was no significant signal cancellation. So it seemed like the easier and nicest approach at this time. But yes, the answer is yes, there is a 10 series.
Okay. And also, were the linear polarization signals strong? Were there good things to see in there?
Well, actually, you can see that in the, well, they should be here. Let's go to, you can see that in the part that goes through the quiet regions, the linear polarization is quite significant. You can see the 2 negative lobes the typical 2 negative lobes in STSW, and the sign change in STSW. You can even see the typical interference pattern here. And when you enter the flash, the signal is greatly diminished due to the magnetic field. That is what is expected from the theory.
Yes. Thank you very much.
Okay, so Phil Judge has a question. He asks, do you have any results at all for the disk center and limb yet?
Again, can you repeat the question?
Yes, he asks for the other positions. So you only showed the plage right now, but do you have any results yet for disk center or for the limb?
They haven't been analyzed in deeply enough. It's a paper is in preparation that shows the data and makes some consideration of the centric tulip variation, but not analysis of trying to infect the magnetic field.
Okay, so we can expect it.
Yes.
All right, Gabe, you want to ask a question?
Yeah. Hello. Sorry about the background noise. My laptop fan is on the fritz, so I hope you can hear me. So thank you for the talk. It was actually really timely because my collaborator Tetsu Anan and others they collected helium-1 observations with the Gregor IFU over a plage region. And one of the main findings that they had was that the field does appear to go, at least in this observation, it's pretty much almost horizontal near the top of the chromosphere. Now it would be nice to see a plot for helium like the ones you've been showing with the formation height of the helium signal, but this is 10.830. So I think that that definitely strengthens your argument for the field being more horizontal near the top. And this plage region was near an active region too. So there the argument was maybe it's, the magnetic field is being bent towards the active region core. How far from this center was the plage region you observed? What's the angle?
I'm not sure right now. It's here
Okay.
midway between the center and the limb.
Okay, great, thank you.
But I don't have in mind the actual number for that distance. But yes, the helium one is also top of the chromosphere, so yes, it should be sampling a region quite close to the one that the magnesium HAO core are sampling. So thank you. Nice to know that there is.
Yeah, he couldn't be here. That he had a different thing, but he I was just trying to plug the paper that I think we just submitted it for review. So maybe in a few months, have a look, because I think it informs the results that you're showing here. Thanks again.
Okay.
Thank you. All right, Phil.
Hi, Tanausú. Thanks very much. Your discussion prompted me to add that at the center of your plage, you're 45 degrees to the vertical. So that implies that it's tricky to say much about the from the longitudinal field about what the configuration of the magnetic field is, except that it's all really unipolar. And then that leads me to mention, I don't know if you've seen a paper on by me, the sole author, on archive. It's coming out in AppJ very soon, but there I argue that almost all the emission we see from, for instance, in your figure, the class 2 right one that we can see there, all that is coming from, it's not coming from cool loops. There are just too few cool loops, and this whole picture of the atmosphere being highly structured by loops connecting from one polarity to another has been overstated for many years. My conclusions are that essentially when you measure magnesium, it is connected to the overlying corona, both in the quiet sun and in the active regions, and that you can therefore use these measurements to determine exactly what you were saying, namely the transport of energy into the corona from beneath. And that's based on your results on your paper, as well as some iris data that I looked at to address the paper by Hanstein et al. In 2014. So if you haven't seen that, I'd be very interested in hearing your opinion on that paper.
Yes, I know it exists and it's in my to-do list to read it.
Sorry, I didn't quite understand. It's not very good.
I know about the existence of the paper, but it's still in my to-do list of reading.
Okay. But it's a really impressive experiment that you guys have done, and I found it very interesting that it was prompted not by previous observations with things like UVSP and other things, but it was prompted by the development of the theory. I mean, that's rather unusual in solar physics. So I think you guys can be very, very much credited with changing a little bit the way we think about starting new experiments. So that struck me as a very interesting part of your talk.
Thank you.
Okay, thanks, Phil. Does anyone else have any final questions?
Yeah, when can you come to HAO, Tanausú?
I don't know when they letting me get inside the US. I tried to go, I mean, I wanted to go last summer, but for obvious reasons, it had to be cancelled.
Yeah. Well, you're welcome anytime.
Well, another question is, when are you going back to HAO?
Yeah, good question. I don't think we know that yet. All right. In that case, thank you again, Tanausú, and thanks everyone for coming.
Thank you, Tanausú.
Thank you
Good
very
to
much.
see you.